So, my previous video was rudely interrupted by the fact that my camera has a limited lifespan and I don't charge my batteries. So, yeah, I guess that makes me not qualified to teach this class. But I'm going to anyways. So, when we left off, abruptly, we were just combining a resistor and an inductor in series with a power supply. This is an AC power supply. VAC provides some variable oscillating sinusoid for a voltage supply. Okay? And this has some resistance R and some resistance L. Now the issue with how this circuit responds is the way that this power supply sees this circuit. We discussed it as the current through a resistor is going to be in sync with the voltage, meaning as we apply a voltage supply, the resistance, the relationship between current and voltage in a resistor is linear, so we're in sync. The sinusoids are going to be in sync with each other. Current and voltage are going to oscillate together. But the issue with the inductor is that current and voltage, well, the current lags the voltage. So what we need is, between these two, with these being in series, here the current and the voltage are in sync. Here the current lags the voltage. Combining them, neither one of them are going to be real accurate. What we will end up with is just qualitatively our, let's say, our VL. Okay, and we'll do VAC and IAC. See, this is the voltage that is supplied by the power supply, and this is the current that is coming out of the power supply and going to the circuit. If we look at the relationship between the two, we have our VAC, it's going to be a nice sinusoid, whereas our IAC will be a phase shifted sinusoid. So here, this, if we were only to have, let's say, have a resistance equal to 0, I'll draw this one in green. So R equals 0 here. What we'll have for this is our current wave will look something like this. Phase shifted at negative 90 degrees. Okay? If we had L equals 0, meaning we have no inductance, there is no magnetic energy that is induced by current flowing in the system, then the relationship will look like this. Okay? Where these two are in phase. So if we have L equals 0, if we have R equals 0, now if we have neither of these equal to 0, then we're somewhere in between this. We will be slightly phase shifted negatively, which means what we're looking at is, we just continue this downward. With no phase shift, we're here. With some phase shift, we start maybe right here. More phase shift here, more phase shift here. It really depends on what is the dominating element that's going to show up here. Is the resistance more dominant in controlling the current? If so, then our voltage is going to be nearly in sync with our AC source. If not, if the inductor is what's controlling the voltage, we will be more out of sync, more lagging. And the more the inductor controls it, the more lag we are going to have, the farther down. So what we'll end up having is maybe a system that looks like this. Someplace in between these two. Okay? Where there is a little bit of lag induced. Okay, now this would probably be more having more resistance controlled. Having more inductance controlled, we would probably start way down here, and it would be closer to this green line than it would be to the purple. Like that. Ah, too far. all we're doing here is by adjusting the resistance and the inductance value, it's not, yeah, it's going to change the overall amplitude, but if we're just looking at the phase shift, how this system moves left and right, we're just looking at how it's affecting that phi value. More resistance means it's shifted more towards being in sync with the voltage. More inductance means it's shifted towards being more out of sync. Now this poses an interesting scenario, because if you remember from the last video, if we just have, I won't draw it as an S, it's actually a sinusoid that's sideways. If we just have a capacitor, then our VAC and our IAC, VAC like this, IAC leads like that. Okay? We've moved this direction. But if you remember for the inductor current lags the voltage. So instead of seeing one where, you know, this point here corresponds to that point here on the sinusoid, what we'll see is doop 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 doop. Pretend that's nice and it looks good. My art skills are getting worse. Is we see this. Okay, where it starts down here, where this corresponds with a 270-degree phase shift. So if we combine these two to one circuit, where now instead of having a resistor and an inductor, now we have a capacitor and an inductor, it is possible to get the full spectrum between a negative 90 degrees and a positive 90 degrees. So if I have, here's VAC, and here is IAC. VAC is going to be just a standard oscillation. And then I will draw both of these graphs on top. Okay, we'll say that capacitance, which means your inductance is 0. Okay, so inductance is equal to 0 here for a green line, and our capacitance will be equal to 0 with this purple line. So what that means is if we took this circuit and we plugged in L equals 0 and threw the cap on the ground, and rage quit science, if our capacitance here is equal to 0, then we end up with the purple curve. If our inductance here is 0, we end up with a green curve. Okay? That's all that means. If we have non-zero conductance, capacitance, or inductance, we will end up with something between these two curves. Now, what is between these two curves? Well, this curve is between these two curves. This one is positive 90 degree phase shifted. This one is negative 90 degree phase shifted. It is possible, with the correct combination of inductance and capacitance, to actually get 0 phase shift, because it's right in the middle of both of them, to which these are in sync, behaving much like a resistance-only circuit. What does that matter? Well, it matters when it comes to power. How much power is coming? Where is this? Are we getting the same power of components at the same time? If you are running an AC signal through a bunch of LEDs and different LEDs are turning on at different times, it's going to display differently when it shows up on a camera or something with a high speed quality. It really does change the dynamics when you have some elements that are going to be shifted. Understanding the relationship between voltage and current, and understanding the time relationship, how that changes with an AC current applied, is really what I'm going to be most interested in you understanding as a part of this course. And your homework problems for next week are going to be about this. Another thing that I wanted to discuss is actual power calculations. So here, the power that is provided from this device to anything is always given by the voltage multiplied by the current. Now here the voltage is not constant, and the current is not constant. Neither of these will ever multiply to a constant value. So how do we come up with a power value? How much power is being provided by the power source? Well, that's an interesting question. If we're going to calculate power, we can give an instantaneous power value, but that's going to depend on us coming up with what is the current, what is the voltage. Instead, we say, okay, I don't really want to know what an instantaneous power value is. Your power value here, if we're going to plot it out, power versus time, for any AC and DC circuit, is going to look something like this. Where this is a sine squared curve, some sine squared curve. Maybe phase shifted in one direction or another, but you will see power spikes where it is increasing power. Now, if your power isn't being absorbed because you have no resistive element, you'll find that it will average to zero. It's not going to be, it'll be more like this. But there are moments where you have zero power that's being submitted through a system from the power source, because it either has no voltage change or it has no current change. So talking about power, if we were to discuss instantaneous power through this system, it'd be kind of ridiculous. There's no use in me saying, well, what power is being supplied at T1? Well, here, this is 0.4 watts. Over here, it's 0.8. It just doesn't make sense for us to sit down and try to instantaneously pick out one power or another. Instead, what we want to do is we're going to say, okay, what is the average? What average power is being provided to this? And an average power is up to interpretation. The formula that is most often used for calculating the amount of power that's coming out of a power source or being used by an element, whatever it may be, is given by calculating a VRMS. Okay, what does that mean? Well, V is voltage. RMS means this is a voltage root mean square. Okay, the idea behind a VRMS value is that your root mean square is going to be dependent on how much power is actually being generated by a system per amount of time. It's an average over an entire cycle. So what you have here, the equation that's given in the book, is VRMS is equal to the square root, no, I do not have this memorized, of 1 over t multiplied by the integral from 0 to t of v squared time. Okay, why is this important? Well, this v squared gets rid of the negative voltage. It means that now we have a positive voltage we're dealing with all the time. We're not providing some weird negative or zero value voltage here. Having any voltage that it is applying to the system is going to give us a positive VRMS, because there is some driving force that is causing the system to behave the way it is. Okay, so we will have a positive value. Once we square it, take the integral of it, multiply it by 1 over t, which, remember from the last video, t is equal to 1 over the frequency, which is equal to 2 pi over omega, which is the angular frequency. By doing this, then higher frequencies means you have lower periodicity, which actually means you have a higher VRMS. Having lower frequencies, higher period means you have a lower VRMS. Okay? Now, when you run these calculations through, multiply this by the current, you can come up with a power value for pretty much any of the elements. The power element that's given in the book is your P average through a resistor is equal to your V squared RMS over R. Why does that matter? Well, this is just P equals VI, where we replace I with V over R. Okay, so this is for a resistor. Okay, you take the square root out of this, perform the integral, you can figure out how much this is. You could also replace the V. We can do the same thing with IRMS to come up with the root mean square current. IRMS is equal to the square root of 1 over T times the integral from 0 to T of I squared T dt. So same exact formula between these two. You multiply these two together, you can get your power RMS value, which is given by this for a resistor. You can calculate it out individually for other elements. These are some important functions that you will be using for your homework assignment. I do care a lot about power. Most of this course is power. We'll talk a little bit about phasers. Phasers is that phase shift that we've been discussing. We'll talk a little bit more about that on Thursday, as well as doing some discussion on Raspberry Pi, which I have yet to figure out how I'm going to do it. So bear with me. Bye.